In this video, we're going to discuss more about how to actually add substituents to chair structures effectively. So we looked at that a little bit in the last video towards the end. And so now we're going to actually work through practically how you'd pull this off. And we have to pay attention to some details like whether or not the substituents added to the ring are wedges and dashes in the flat structures. So let's just go ahead and get into it. So, sorry, my computer's just being a little slow today. Okay. So what we want to do is we want to take a complicated molecule like this, where we've got methyl groups, we have chlorine atoms, we've got ethyl groups, and OH groups. And so what we want to do is be able to convert this into a chair. And so when we convert into chair, I mean we draw the chair structure and then we attach the groups appropriately. So for example, one possible answer could be this. Okay, so I did that pretty quickly. Obviously, I've been doing this for a while now, but this is what I want us to be able to do, is to look at chair structures, flat structures, and then convert them into a one of many possible chair structures. And I want to emphasize before we get going into this that this is one of many answers. And there again is the issue with molecules. They exist in 3 dimensions. And so just one kind of rotation of them could look different than other rotations of the exact same molecule. And so it takes quite a bit of skill to be able to reconcile when molecules are the same or different. That's not for us to worry about right now. For us to worry about, what I want us to be able to do is draw one possible structure. Don't worry, I will be the one grading them and looking to make sure that they all kind of are in line. Okay, so how did I do this so quickly? So a few steps. And these are just steps to get us started. After a while, you'll develop some workflow that works best for you, hopefully. But the first step is that we need to draw our favorite chair. And what I mean by that is there's going to be one depiction that you're sort of most comfortable with, that you can draw quickly without kind of making the flaps look too skinny or too tall or too awkward. So I don't really mind. I guess I tend to go towards this one, or I do this one too. It's all whatever you're comfortable with. It doesn't matter. You get to pick this. Okay. Number 2 is you decide where to put one of the groups. So I'm going to call this the first group. Now that isn't like the highest priority group in naming. It's not like the biggest group. It's just whichever group you want to add first. So you decide where to put the first group, and it can be anywhere on the ring, just as long as it's attached to a carbon on the cyclohexane in this example. And then step 3 is you want to add the remaining groups so the relative position is correct. And then the last thing that we'll look at today is we want to check that wedges, I guess wedged in quotes, groups are up in the chair structure and vice versa. So we'll look at that in more detail towards the end of this lecture. So we have these steps: draw our favorite chair. We're going to decide where to put the first group. It can be anywhere. Then we add the remaining groups so that they're in the correct relative position. And then number 4 is we're going to make sure to account for wedges and dashes that were part of the flat structure, make sure that they're correct in the chair structure. Okay, so how do we deal with wedges and dashes? Well, how do we deal with wedges and dashes in chair structures? We don't draw them. I guess I should have capitalized the don't. Okay, so we don't draw wedges and dashes in chair structures. If we had to draw wedges and dashes, I kind of showed you previously that what that would look like is you would actually only consider the bonds inside the ring, where the lower 3 are wedges and the upper 3 are dashes. And we could do that for either chair structure. But that's it. And even that is not very useful once people don't do this unless they're learning chair structures for the first time. So I was just trying to give you a sense of the perspective that these chair structures would carry. But I'm not going to actually draw wedges and dashes like this in any of the chair structures that we want to depict for points. We just remember that the lower 3 bonds and the lower 2 atoms are in front, the raised 2 atoms and the raised 3 bonds are in back, and then the furthest left and furthest right atoms are in the plane of the paper. And we talked about that before. But practically speaking, we don't use this when we're actually drawing chair structures. So we don't use them. But wedges and dashes are in flat structures. So they are in the flat structures. So for example, we could have something like this, and they need to be translated. Okay, so we need to recall that these things are in our flat hexagon structures, and they need to be translated over into the chair structures. Otherwise, we're not accurately depicting our molecule. So what we need to do is convert this into a chair. So the chair, and we'll get to this later, we'll show this later, but we never draw wedges and dashes in chairs. That is to say, if I do something like this, where I draw a wedge and a wedge for like axial and equatorial positions, that is incorrect. Our substituents that are directly attached to the ring should not have wedges and dashes in our chair structures. That's an important point to make. Okay, so what I want to do is consider what this molecule would look like as a chair structure. So let's do that. Number 1, draw our favorite chair. Let's go ahead and do that. We're going to pick where to put the first group. Now here's what I do, and I really like it, is I'm going to like have a little shape, maybe a star on my first group. So there's the original hexagon structure that I added a star to. And I'm going to do that. I usually pick the left hand or right hand most carbon. And I find myself picking the right hand most carbon. Either one is fine. They're both effective. Now what we want to do is add both positions. So draw the wedge and dash on the chair. Excuse me, screwed that up. Draw the axial, we don't draw wedges and dashes on chairs. Draw the axial and equatorial on the chair. So here's my equatorial and here's my axial position. Okay. So the way that chair structures work is that wedged groups on a flat structure are up on a chair structure. And vice versa. That is that if we have dashed groups on a chair, on a flat structure or a hexagon, those dashed structures will translate into down structures in the chair structure. So what do I mean by an up group, an up group, not an up structure? What do I mean by an up group and a down group? Well, let's go back to our starred carbon here. So I'm going to draw the equatorial and the axial positions on that chair structure. So we have our equatorial and our axial, and that corresponds to this wedge, which is next to another wedge. Okay, so we're focused on the starred carbon. The starred carbon has a wedged group. The wedge should be up. Now we get to select one of the two positions at the starred carbon on our chair structure. We are going to put a methyl group or a CH3. Maybe I'll write that out here so you can follow it. I need to add a CH3 to one of those positions, either the equatorial or the axial. The axial group is pointing straight down. So if I had to choose whether or not the axial or the equatorial was up, I would choose the equatorial to be up. So the equatorial position in this case is my up group. And the reason why I can tell that is, well, there are always two positions attached to any carbon on a chair structure, an axial and an equatorial position. One of them has to be the up group. The other one has to be the down group. How do I tell? Well, I usually just look at the axial position. That should tell me whether or not the equatorial is an up group or a down group. Here, the axial is pointing straight down. So the equatorial position is slanted upwards, so that's my up group. So I'm going to add a CH3 at my equatorial or up group. Now what about my axial position? What do I do with that? Well, for every wedge, there must be a dash. That's going to be an important concept in this module. This is the first time I've said it, but for every wedge, there is a dash. And for every dash, there is a wedge. So it's just saying going in both ways. So why do I say that? That's kind of an awkward phrase. Well, what I'm saying is that if we look at this position on our cyclohexane, recall that a tetrahedron, one of my favorite ways to draw it anyway, is with two straight lines, two in-plane lines, one wedge and one dash. And the wedge and the dash are overlapped with each other. So for every wedge, and there's a wedge here drawn as a CH3, there must be a dash. Now, why didn't I draw the dash? Well, let's think about the things that we don't draw when we draw bond line structures. One of the critical things that we avoid drawing is hydrogens, are hydrogens that are attached directly to carbon. So the dash group here is going to be a hydrogen atom. So the hydrogen atom is implicit, its existence is implied in a bond line structure. Now, what about a chair structure? Do we need to draw the hydrogens attached to carbons? And the answer from my perspective is do whatever is easiest for you to understand the situation. The important thing is that we accurately depict molecules that are parts of chair structures. And what that means is that if it helps me to understand the chair structure drawn above, and in particular, this dashed hydrogen, which is going to be axial in this depiction, okay, I should draw it if it helps me understand the molecule. Okay, so I added the hydrogen to that axial position down. It's important that I add that or erase that axial position, because if I just leave it blank, it could be interpreted as a one carbon substituent, a one carbon chain, a methyl group. So my axial group, my hydrogen is down, and that's because the H was a dash. I didn't need to draw it in my original structure because of the rules of bond line structures, but it exists, it is real, and I should draw it if it helps me understand the chair structure better. Okay, so we've just covered our first position, the starred position on our chair structure. Now we're ready to add the other positions. I think what's coming next could be one of the more trickier things about chair structures, and that is adding substituents or adding the remaining groups so that we have the correct relative position. Okay, so what I'm going to do is just go on to another page. I'm going to redraw our molecules again. So I've redrawn the chair structure, and there's the starred carbon, which matches that carbon. Remember, I could pick any of those carbons to kind of be the substituents. So here's kind of a little trick that can help us determine the relative positions. So the goal here is to add the other CH3 so that it is positioned correctly. Now, what I mean is if you look at that CH3, the second CH3, if you look at that CH3, it is right next door to the carbon atom with the star, right? It's right next door, one carbon away. So if I had a bunch of chair structures, I'm going to do this quickly. If I added that position here, that would not be correct. It's too far away, right? I mean, it's too far away from the starred carbon. We left a little bit of a carbon spacer between that group. Now, similarly, if I put it at the same position, that would not be correct, right? If I drew it as the axial position, that would not be correct, because that would imply that this second CH3 is attached to the starred carbon, and it is not. If we go back to our original structure, the star was over here, and that second CH3 was next door to it, but not at the starred position. Okay, so that would also be incorrect. Okay, now there's another way that you could get this wrong. So we know that it's right next door, but there are two positions that are right next door to the starred carbon atom. And it does matter which way you proceed. So what I'm saying is that at the starred carbon, there are carbons next door here and here. So I could have a position where if I want to label that second carbon with a square, and I'll leave the wedges out for a second, I could put the square at this position, and maybe I will, okay, or I could put it in back, and I chose my words back carefully there because I know the raised bonds are actually in back, and I could put the squared carbon at this position. Now, once we know which of those two squared positions to add the CH3, we can go back and realize that that second CH3 is also a wedge. So of the two groups attached to the squared carbon, we want to put it in the upmost position. Okay, but we can't get there yet. We have to know which of the squared carbons we're going to pick to add the substituents. Well, it turns out that there is one, well, actually, they're both kind of correct in this one instance. I didn't pick the best first example. But in most cases, there's one correct answer, and the other answer would provide you with a stereoisomer, which we'll talk about what stereoisomers are as a big part of the class starting at the end of this module. But suffice it to say, there is one correct answer. So how do I know which one is correct? Well, I'm going to kind of show you a trick where we're moving around a chair structure. So if you look at our flat structure, if we're starting at the star, we could move clockwise around that ring structure. That is to say, if I start here, this would be next door, then this would be 2 carbons away, 3 carbons away, 4 carbons, we could go around the ring in that direction. Okay, so what I'm saying is if we go down to the squared carbon, that would be our first carbon if we moved clockwise around the ring. So I'm saying we're going clockwise around a flat structure. So what does that look like for a chair structure? With a chair structure, clockwise rotation, or it's not rotation, clockwise movement or encircling around a chair structure looks like this. So clockwise movement is going to be this way, then 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 this way. This is a really important concept. So what I'm saying is that if we start at the starred carbon and we move clockwise, one bond, we are going to bump into the group in front. So this part of our notes needs stars because this is a critical part in identifying where groups go accurately on chair structures. If we get this wrong, we draw different types of isomers of chair structures, which are really interesting to consider, but really complicate our lives. So if we're just able to go and recognize what clockwise movement around a flat structure means in a chair structure, which is shown in this little page of notes, we'll be able to accurately determine where to connect the various groups on our chair structures as they get more and more complicated. Okay, so I've added a group to my chair structure, or I haven't added anything. I've recognized where the squared carbon is. So let's go over, we'll draw this again. So there's the starred carbon. Here's the squared carbon. And now in this depiction, we know that this is the starred carbon and the squared carbon. And I should mention the beautiful thing about the clockwise movement is that it holds up no matter which depiction of the chair structure that you're showing. So if you have one flipped version or the other flipped version, it will work in both cases. So the squared carbon has been identified. Once we identify a carbon, we draw the 2 substituents that are going to be added at that carbon, because that allows us to see which is an up group and which is a down group. Now, if you recognize the wedge here is, the wedge means up because wedge. So when we attach the CH3 to the squared carbon in our chair structure, it needs to be at the more upwards facing group. I always go to my axial position. You see the axial position is clearly pointing straight up, so I could add the CH3 there. Now I need to either erase the equatorial substituent in this case, or I could simply add a hydrogen to remind myself that for every wedge, there must be a dash. And I could even add the hydrogen at the starred position too, so that I can see. So this is an accurate depiction of a chair structure for that molecule that I've shown on the left, which has 2 methyl or CH3 groups with wedges. I could do another example. Let's chair this structure again. Now, what I want to do is emphasize in this example that I could change things up and still get a correct answer. Okay, so let's say that I draw this version of the chair structure that happens to be my favorite. And Let's say when I pick where to add the first carbon, I pick the most difficult position on the ring to add the substituent. These are things that work for me, having taught this for 8 years, and before that being in grad school. But as you're just learning, I would not recommend this. Okay, so I'm going to make this my starred carbon, and if that's my starred carbon, my equatorial substituent looks like this, and this is that weird axial substituent that gets cut in half by the lower front bond. Okay, so I have my 2 positions added. Now I know that in both cases, my CH3s haven't changed. They need to be the up-facing group. And there is a hydrogen, okay, facing down because the hydrogen is the dash. I'm gonna go ahead and just add that hydrogen to my starred dash. Okay, so now what I need to do is traverse the ring in a clockwise direction because I wanna go down 1 bond to my square, and that's just a clockwise, that starts a clockwise rotation around the ring. So clockwise rotations are going to go like this and so on. And what that means is that this position, my right-handed carbon, is going to be the square. Okay, so I get to add both positions there, and I've cut my CH3 in half. That's okay. I mean, I'd prefer it if we didn't, but it's okay. We started in an awkward position. We're going to get a few awkward bonds drawn. Okay, so we've got an up and a down substituent. The up is clearly axial in this case. And so we have a CH3 and an H. Okay, so it's difficult to see, it is, but these 2 structures, and let me highlight them so you can actually see what I'm talking about. These 2 structures are identical. We've just kind of rolled the molecule around horizontally, but they are identical. In the next lecture, I'll use 3D models so that we can see that a little bit more effectively. But just at this point, if you don't see it, trust me. This is another example of where there's just multiple structures that can be drawn to depict a flat hexagonal structure. In fact, in both cases, my starred carbon was equatorial. Can I pick an example where my starred carbon is axial? Absolutely. So we could do another example of this. There are just so many ways to depict chair structures. I'm going to depict the chair structure shown this way, and then I'm going to pick my first group to be added at this position. I would always recommend adding your first group at the furthest left or furthest right side. That's just my experience, seems to be the easiest. But again, I'm just trying to show you there's multiple ways to draw these things. So we've done this position before. Where's my axial and equatorial positions? My axial is clearly pointed straight up, whereas equatorial then must be pointed straight down because only one can be up and one can be down. Moving clockwise around the ring is going in this direction to a square. And then I'm going to add here and here. H is down as axial, and then the CH3, and I just kind of flip the CH3 label because I like to show that bonds happen to carbon, not to the 3 hydrogens from the rest of the ring. So, but I'll be pretty loose in terms of being strict on that grading, at least early in the semester. So anyway, in this case, what I did was I added my substituents such that the squared carbon was now equatorial, and the squared methyl group, excuse me, and the starred methyl group, or CH3, was axial. Now, is this a different structure? It turns out no. How these structures now differ is in a chair flip. And we'll get to chair flips in the next lecture, but remember that I kind of hinted at chair flips flip everything, axial to equatorial, okay? And so our starred group went from equatorial to axial as a result of a chair flip. And if you draw a chair flipped version of a structure, because conformational isomerism is fairly subtle, we consider them the same. Again, my goal here was to just show you follow the rules. That is, draw your favorite chair structure, identify where the first position goes, draw the axial and equatorial groups at that position, and add your substituents such that up is up and wedges up and dashes down, and then add the remaining groups by accurately traversing the ring in a clockwise direction. Okay, so that would be, those rules will hold up whether or not you pick one group or another group to kind of be whether you pick the starting position, the first position, to be furthest to the right or furthest to the left. That way everybody gets the same answer, even if their chair structures look different. Okay, so that is kind of how I approach attaching substituents. One thing that you might want to do using those templates that I posted to the learning module is to kind of go through and practice drawing all the axial and equatorial positions and identifying whether or not they're up, down, or would be wedges and dashes in a flat structure. So for example, just as some extra practice, we could consider like the axial positions first. And so these three are up, and so they would all be wedges. These three are down, so they would all match up with dashes on the flat structure. And then I won't flip this chair, but I will draw the equatorial positions. When I draw the equatorial positions now, it gets a little bit harder to see whether or not they're up or down or wedges and dashes, but it actually alternates, just like we see, we go from up to down to up. In the axial case, we're going to alternate, and we can use the axial positions as our guide. So we're going to start here and write D for down, U for up. So it goes up, down, up, down, up, down, up, where U stands for up, and that matches a wedge, and D stands for down, which matches a dash. So that is how I add my substituents to rings. And what I want to do is just start to glimpse into what it's like to flip the chair, just so that we could kind of see this. We've talked about doing chair flips and what they are, but let's just look at very briefly what it does to kind of the wedges and dashes on a ring. So chair flipping. Again, this is a conformational isomerism. Which is free rotating bonds. And it's the sigma bonds inside the ring. Okay, when we do this, all axial go to equatorial. All equatorial go to axial. So all of this stuff flips. But there are some critical things that don't change. And the critical things that don't change or don't flip is up and down. The up and down doesn't change, and the relative position doesn't change. Okay, so the up and down doesn't change and the relative position doesn't change. So I'm going to pick a challenging structure and just show you what happens when we do a chair flip. Okay, so we have this structure, and I'm going to draw the starred at this position and the squared at this position. And I'm going to consider my methyl groups, each pointing up, my hydrogens, each pointing down. One hydrogen's axial, one's equatorial. Okay, then what I want to do is a chair flip. Now, when we do a chair flip, the first thing that happens is we flip the, flaps. So the left-handed sort of pucker or flap was up and is now down. We'll look at more details on this in the next lecture. I'm just trying to give us a preview. And then this pucker was facing down on the right side, and now it's facing up. Okay, So the first thing we have to recognize is that axial and equatorial flip, sure, but let's not worry about that right now. Let's worry about the things that don't change. The relative position doesn't change, and the wedges and dashes don't change. So my point is that if this was our original structure that's in its flat depiction, that does not change when we do a chair flip. Chair flipping only affects the chair structures. It does not affect the flat structures. So this structure is unaffected by a chair flip. That is to say, our wedges stay wedges, our dashes stay dashes. The six-membered ring hexagonal structure does not change as a result of a chair flip. Okay, the other thing that doesn't change is the relative positions. If you notice, the squared carbon was the carbon that is furthest to the right in our chair structure. That does not change. After we flip the flaps, and the right-handed flap, which was pointing down, is now facing up. That furthest carbon to the right is still our squared carbon. And going one direction counterclockwise now gets us to our starred carbon. Another way of thinking about it is our upper right carbon is still the starred carbon in either case. It just looks different because we've kind of freely rotated and done some flipping. Now, what did change? Well, if we add the two groups to either of these positions, what we have to recognize is now the CH3 that was attached to the square is now axial. Why? Because it has to stay up. It has to stay a wedge. And then on the starred carbon, the CH3 is now equatorial. Why? Because it has to stay up, because it has to stay a wedge. The wedges and dashes in the flat hexagon structure do not change. It's just that when we flip the flaps around, we have to change the equatorial and the axial so that the groups stay up if they were originally up, or stay down if they were originally down. What that means is that the hydrogens conversely flip axial and equatorial from the original structure. Okay, so that was a quick preview into what it looks like to do chair flipping. That was a longer look at the first part into how to add groups to chair structures. Use those templates as the guide. Start to practice this thing. These are rules where if you don't study it until the night before, it's exceedingly difficult to figure out the answer to the question of like drawing a chair structure from some flat hexagon structure. Okay, it's just really hard to do the night before. So learn this stuff now. Screw up early, make mistakes, ask me questions, ask your tutors questions, so that we can get these things corrected. And then when you see the problems, you're like, oh, you know, really, this isn't too bad. This isn't rocket science by any means. It's just we need to know a few rules, and we need to understand a perspective or a way of kind of thinking about these molecules in 3 dimensions, which is all chair structures is. So until next time.